Any questions about anything? I want to do one more example of LU decomposition, especially since I screwed it up in class and I just sent you out the video. Okay. So I want to do one more example, make sure we're all on the same page with how it works. And then I do want to talk about two more theorems real quick about stuff that we've talked about, and then we'll have a little bit of a chat about the exam. So, any questions at all? Yeah,
on the exam review, can you go over number 8?
Sure. See if I can pull up the exam review without having to do it on the computer here. It is one thing about everything being interconnected. Take my phone out and get the problems. Ah, okay. Oops. So this one has a matrix with letters in it in different spots, but zeros in a bunch of other spots. 0D, 0E, 0, 0, 0, F, 0G, 0, 0, H, 0. Okay. So it says, have this 5 by 5, and it says that show that it's, pardon me, show that it's singular, show that it doesn't have an inverse for any of the values of the variables, right? If it's going to have an inverse, when you row reduce it, what do we have to end up with? If we were to go through row operations and row reduce it, if it does have an inverse, what do we have to end up with at the end? The identity, right? Yeah. So the first thing that I would do in this particular case is what would happen if you don't get the identity. So let's look at this B. Is it possible for B to be 0 and then be able to row reduce it and get the identity? No, because I'll get zeros all down this column, right? And then I can't possibly get a pivot in that column, right? I'm going to have pivots in all 5 columns in order to show that this is going to have an inverse. So B better not be 0, right? Likewise, what else? Looking at a row rather than a column, what else better not be 0? You should be able to tell me 2 other ones quickly that can't be 0 to start with. If I look at the rows, A and H, right? Because if A is 0, I got a first row of zeros, and again can't get a pivot in that row, right? And if H is 0, I can't get a pivot there either, right? Okay. So if I assume here that if A is 0, then it certainly is singular. So let's assume that A is not 0. We'll also assume that B is not 0. I can get rid of the D then, right? We do row operations, we can get rid of the D if the A is not 0, right? I would divide by A and then multiply by a negative D. You agree? Okay. So let's just do that without getting ones and worrying about it. Let's say we have negative A. Oops, sorry, try that again. Negative D over A, row 1, plus row 3, and replace row 3. That gives me 0, 0, 0, E. The E didn't change, did it? At that point? 0, 0, 0, F, 0, G, 0, 0, 0, H, 0. Right. So I didn't write it all down, but the argument to start with is that if A is 0, it can't be invertible. Hello. If A is 0, it can't be invertible. Assume it's not 0. If it's not 0, then we can kill the D off, right? You get a 0 there. So far, so good. Okay. Now let's look at the third and the fifth rows. You already told me that H can't be 0, or otherwise it's not invertible. What can we now say about E? Yeah, E also can't be 0, right? If E is 0, then it's also not invertible. But now that if we assume that E is not 0, can we kill off the H? Yeah, right? I can do the exact same thing that I just did for row 1 and row 3, right? with different letters, I can multiply row 3 by negative h over e and add to row 5. And that'll kill off the h. Yeah, maybe.
Why did we go to the row of the E, the column of E and H instead of the C and the
I was working with the ones that just had a single letter in them.
A? Okay.
You could do the other one, it just take a little bit longer to get there. You could, and also if I try to get rid of the, I could get rid of the C this way, and then but that would bring the G up. So it's a little bit easier to work with the ones that just have the single letter. That's the only reason why I was playing with those. So again, I didn't write down all the steps, but the first thing we have to assume that A is not 0 before I could do this, right? Before I can say I can divide by A, and then do the same thing with the E. Now do negative H over E row 3 plus row 5 and replace row 5, and then nothing changes except the final row becomes all zeros, right? So no matter what the values of the variables are, we get this is going to be a row equivalent. Row equivalent meaning that there's a sequence of row operations that gets me to a particular matrix. This will be row equivalent to something with a row of zeros in it, which means it's not invertible, no matter what the letters are. Do you have a question, Ben? No. I thought you were raising your hand. That's okay. No worries. Yeah, Devin.
Is there a notation for row equivalent, or would you just write it out?
Usually, if you have some books will use that. Some books will use that. I usually just say is row equivalent to. Just write it out in words. But some books will use that. I don't think they use that notation in our book. But there are books that will use the is similar to notation from geometry. That was is congruent. Not quite congruent. But it's also another way. Congruent usually has the little squiggle and then an equal something to it, right? This is also an alternative notation for congruent. This one okay? All right, so again, the whole idea here was to get to a point to say I can't get the identity from row reducing no matter what, right? If the A was 0, I can't row reduce to get the identity. If the A is not 0, I can kill off the D. Then the E has to be not 0, otherwise I can't get row equivalent to the identity. But if the E is not 0, then I can kill off the H. And then we can't get row equivalent to the identity. So no matter what we do, we can't do row operations to get to the identity. Is that what you wanted to see, Lee?
Yeah.
Okay. So this actually leads us to one of the things I want to talk about today. So I'm going to do it first, and then I'll go back and do an LU decomposition example. Make sure we're all on the same page with that. I would suggest at this point finding a blank sheet in your notes, because we're going to add to this theorem over the course of the semester. I like to call it the mega theorem. At some point, we're going to get 20 lines long. Okay, so I would write it on a separate sheet and then keep track of where that sheet is, because we're going to refer to it later on. As a matter of fact, we'll refer to it back when we get to determinants. So right now, we're just going to have 5 things we're going to write down, but we will add to it as we go along. So, actually, we might write more than 5 things down right now. So, the way this starts off is it says for an n by n matrix A, the following are equivalent. When we say the following are equivalent in mathematics, what we mean is that from a logical standpoint, the statements that we're going to write say exactly the same thing. Most of the times, your theorems are presented in an if-then form, so if you assume the first part, the second part follows. Right? Okay. The other way around is sometimes you also talk about if and only if, means that the if in the then, and then if you reverse it, it's also true. That's if and only if, right? If implies the then, and then if you flip it, it also gets the true statement as well. That's if and only if. This is basically just a whole big long list of if and only if statements. One thing implies the other and vice versa. Okay? All right. So the first statement that we're going to write is that A is invertible. Why did you do that? Go away. Okay. So what we're going to collect here over the course of the semester is a bunch of statements that all say that A is invertible. So one of the things that we just mentioned in the previous example is that the matrix is row equivalent to the identity matrix, or said another way, the reduced row echelon form of A is the identity matrix. But we've had some other things that we've talked about as we go along. We've talked about homogeneous systems. I'm not done with this particular statement. We've talked about homogeneous systems. What's always a solution to any homogeneous system that you come across, no matter what? What can you always plug in for the x vector? Zero vector, right? It's always consistent, but if your matrix is invertible, do you get more than that one solution, or do you just get that solution? You just get that one solution, right? Because I can multiply both sides by A inverse to get x by itself, right? And then with just A inverse times 0 will be 0. Okay? So we say that this one has only the trivial solution. Another one talks about any system, homogeneous or not, change it to just some arbitrary B. Now, what I just mentioned before to show that we could have this only has the trivial solution, we could multiply both sides by A inverse, if A inverse exists, right? Agreed? Okay. Well, if A inverse exists, I can multiply both sides by A inverse, which means I can always solve for x, right? Okay. So another equivalent condition to be invertible is that this is consistent for every n by 1 matrix B. No matter what I put on the right-hand side, I can always solve it. Now, remember, consistent means that it could have more than one solution, but it has at least one, right? But we just said, how did we solve it? What is one method for solving this? I could multiply both sides by A inverse, right? Do I end up with more than one solution or just exactly one solution? So if I multiply by A inverse, I say x has to be one thing, right? So that says that solution is also unique. So this has a unique solution. And finally, the last one we're going to write down today is that we've talked about doing that sequence of row operations and keeping track of what they are and creating those elementary matrices, and then going back and writing the matrix as a product of elementary matrices, right? we did that for inverses, but we also did it when we were finding that lower triangular matrix in the LU decomposition. Right? Okay. So 6 says that A can be written as a product of elementary matrices. So right now we've got lots of different statements that say the exact same things, and we use them in different contexts. We used 2 to help us find what the inverse was algorithmically, right? Using Gauss-Jordan, we're reducing it to the identity matrix, and then getting the inverse on the other side. We'll use 3 when we start looking at sets of vectors and determining whether or not they have a special property. Okay. We used 4 and 5 basically to talk about the inverse method for finding a solution, and 6 we've used to write the lower triangle to find that lower triangular matrix in our LU decomposition. Okay. So all of these are important. We use them in different contexts, and we'll have other ones that will pop up that we're going to use in other even more contexts. Okay. So we'll have lots of things to pile all together. But like I said, keep this separate because we're going to add to it. We've got at least 14 more things to write down on that list. And I'm not joking. There's at least 14 more things to write down on that list. Okay? But again, they're going to pop up in different contexts. One of the contexts that's going to pop up in the next chapter talks about determinants. One of the things that pops up in vector spaces is linear independence. Okay? There'll be lots of different things. And we also will do what are called row spaces and column spaces of matrices. There's all sorts of things that will pop up in vector spaces. We'll have something that comes up with eigenvalues and eigenvectors later on. We'll also have things that come up with linear transformations, all of these things. There's different contexts that we're going to learn about, but invertibility pops up in all of them. Okay. It's a very, very common theme as we go along. All right. I do want to mention, before I talk about the LU decomposition, we mentioned before that what are your 3 possibilities for number of solutions for any system of linear equations? What are the number of possibilities for solutions?
3.
Well, 3 is there are 3 possibilities, right? What are they?
None.
There's none, exactly 1, or infinitely many, right? It's either inconsistent, there aren't any. It's consistent and unique, or it's consistent and there are infinitely many. But we never proved that those are the only 3 possibilities, right? So the way the proof goes, well, we're actually stated as a different theorem here. If, I'll say B1 and B2 are both solutions to AX equals, I'll give it a C this time since I used B's already. If B1 and B2 are both solutions to AX equals C, then this system has infinitely many solutions. If we have 2, I should say they're, let me say they're unequal to start with. Just to make sure my statement's accurate. Let's make sure I do two distinct solutions here. So B1's not equal to B2. Then we get infinitely many solutions. Yes, it should be written on that. Right? No, you can go back to your original notes for this. Yeah, it was the big one here that should be on the separate page because we're gonna come back to adding to that list. This is just I was dovetailing it from this part here. You can go back to your original notes for this one. All right. What does it mean to be a solution? Just generally speaking, from algebra class, any algebra class you've ever had, what does it mean to be a solution? Yeah, there you go. It makes a true statement, right? You plug it in and it makes it work, correct? So if B1 is a solution and B2 is a solution, what equations can we write down? Here's my system. Here's my solution. Yeah, go. Good. Good. That's what it means to be a solution, right? You plug it in and it works, right? You plug it in, you get a true statement. Here's where we're going to play with a little bit of arithmetic. What happens if you subtract the two solutions? What do you get? Good. Oops. Forgot to write a verb. Yeah. If I take AB1 and AB2, subtract those two things, both of them are equal to C, so I get C minus C. Which is going to give me the 0 vector. So subtracting gives me the 0 vector. What can I do here with the A? I can pull it out, right? It's a matrix arithmetic property, right? It's a distributive property. I can pull it back out. So we get A times the quantity B1 minus B2 equals 0. Okay. I have solutions to the original equation. I now have an original system of equations. I now have a solution to what type of system? I don't have a B here or a C here anymore. What kind of system now do we make? Homogeneous, right? The B1 minus the B2 now is a solution to the homogeneous system, isn't it? Because of the 0 part there, right? We also said that this is not equal to 0, right? The B1 minus B2 is not equal to 0. So now I have a non-zero solution to the homogeneous system. Okay? Yeah. Take any real number t, doesn't matter what it is. Actually, it doesn't have to be a real number as long as we're in a set of scalars, but for right now we're just doing real numbers. Take any scalar times b1 minus b2. If I do a times t times b1 minus b2, what can you do with the t? So from an arithmetic standpoint, what can we do with the t? I could distribute it. What else can I do with it? Yeah, I can move it out in front, right? And put it out in front first. We can do t times a times b1 minus b2. That was one of our properties of scalar multiplication, right? But what did we just say that a times b1 minus b2 is? 0. And if I take t times the 0 vector, we get 0 vector. Yeah. So how many solutions did we just create for the homogeneous system? Infinite, right? Any real number t times the vector b1 minus b2 gives me a solution, right? All right. How does this help us get now infinitely many solutions to the original equation, right? This gives me we definitely now have infinitely many solutions for the homogeneous system, right? Actually, we've actually proven now that if we have distinct solutions for a homogeneous system, then we have infinitely many solutions for that homogeneous system. We just proved, okay? How can we help us now to get to infinitely many solutions to the original system? Well, we do a little trick. Let's consider B1 plus T times, I'll write it this way, B1 minus B2. I could have done B2 minus B1. Doesn't really matter. Take the solution to the any solution to the homogeneous system and add it to one of the solutions to the original system. Let's multiply it by A. What can I do with that? Now what can I do with the A? Distribute it, good. What does the first one equal? B1 was a solution to the original system, so it equals C. The second one's a solution to the homogeneous system, so it equals 0, and we end up with C. So that B1 plus T times B1 minus B2 is a solution to the original system for all T. So we generated infinitely many solutions. So if we have two distinct ones, we can generate all of them. So for those of you in differential equations, or if you've had differential equations, this is how you go about solving non-homogeneous differential equations. I don't know where you are in differential equations with solving right now. But if you have a non-homogeneous equation, there's a two-step process. You find a solution, you find all the solutions to the homogeneous system. Okay. If you've done anything with differential equations at all, even in calculus class, one of the things that you see, like for example, if I at y prime is equal to y is a pretty classic differential equation. What function do you know is its own derivative? E to the x, right? But also if I multiply e to the x times any constant, it's its own derivative, right? So that would give me a solution for all of these things. Notice I can convert this to a homogeneous equation and say it's equal to 0. Right? This would be a solution to the homogeneous system. It involves y and y prime. Nothing over here on the right-hand side. A non-homogeneous system would say change this to a different variable. Right? Maybe you have it with something with x's in it. Non-homogeneous would be something like y minus y, or y prime minus y equals x would be a non-homogeneous thing. Right? And then so the first step is solve the homogeneous system. That gives you the infinite part, and then your next step for the non-homogeneous part is find one solution and use that as what's called a particular solution. So it's broken up into two pieces. You get a particular solution, like in this case, the B1 is a solution to AX equals C. B1 minus B2 represents a solution to the associated homogeneous system. Multiply by a constant, and you get all of the solutions for the homogeneous system. Put it together, you get all the solutions to the non-homogeneous system. This pops up in differential equations. You haven't done it already. I promise it pops up. Anyway, the whole point of this is 3 choices, 0, 1, infinitely many. That's all you get for solutions to the linear system. Okay. Second point is what the form looks like. Particular plus homogeneous solution. That's how the form pops out. And that's what's important when you do diffie-Q. Anyway, I wanted to make sure we went through that proof because that result is very important to talk about. You can't have exactly 3 solutions, for example, right? It's 0, 1, or infinitely many. That's all you get. Any questions on that at all? This type of proof is it's a nice one because it's actually very constructive. It tells you what the solutions have to look like. Or I should say what the solutions should look like when you're done. Okay. All right. I wanted to do one more with the LU decomposition, make sure we were all on the same page with that. Since I messed it up last time, I'd rather not mess it up again. Pardon me. Let's say we have the matrix 2, 0, 0, 0, negative 3, 1, 10, 12, 3. I want to find an LU decomposition. Again, it may not be possible to find an LU decomposition. One way that it's not possible to find an LU decomposition is if you have to do a permutation, you have to do a row swap to make sure that you can get a pivot in the first row, for example. Then technically you have to do what's called a permutation matrix and then an L and a U. Okay. So for example, if these 2 rows were flipped, you wouldn't be able to do an LU decomposition. You'd have to do a row swap first and then do an LU decomposition. Yes.
Would that, strictly speaking, change anything?
It just changes how the algorithm would work for solving the system afterwards. Because you'd have to make sure that you knew where the swap was to start with. Yeah. That's what changes. Yeah. The actual finding the L part and the U part, no, that part doesn't change. It's just that you'd have to know what the swap was at the original spot. All right. So in this case, again, first thing we want to do is what? Yeah, we want to row reduce it. So the first thing we'll do is good. Yeah. Divide row 1 by 2. Again, technically, we don't have to get 1s down the diagonal for our upper triangular matrix. It just needs to be lower times upper. The reason why we get 1s is because it parallels what we do for everything else when we row reduce. Okay. Right? Because you're trying to get 1s down the diagonal. But technically, as soon as you split it into a lower and upper, that's an LU decomposition. So there are multiple LU decompositions for the same matrix. I'm telling you this because I'm going to show you something on R real quick in a second, and it won't look exactly like what we end up with. Okay. All right. Next step is what? Good. Negative 10 row 1 plus row 3, replace row 3. That one was easy because there were zeros in the other 2 entries, so I didn't have to do anything with the other 2. It just made 12 and 3 in that third row. Next step. Yeah. Negative 1/3 row 2, replace row 2. So I'll change it to a negative 3 and a 1. Right? And then finally, should be, well, maybe 2 more steps, I guess, technically. Next thing we need to do is, good. What do we get here? 4 plus 3 gives me 7. We agree? Okay. Again, technically, we could stop here. This is upper triangular, isn't it? So this could be the U, right? But if I wanted to go ahead and finish off putting it in row echelon form, what would be the last step? Yeah, do 1/7 of row 3 and replace row 3. Again, you don't have to get ones down the diagonal on the U to make it an LU decomposition, but it mirrors exactly what we've been doing for every other problem, right? Get ones, get 0 below it, get ones, get 0 below it, right? It's doing the row operation, the row reduction thing. So just for reinforcement standpoint, it makes sense to do it that way. All right, so that's your U. How do we find the L? Yeah, we do the inverses of all the elementary matrices that gave us those row operations, right? So what would be your first elementary matrix that undoes that first row operation that we did? Good. All right. 2, 0, 0. Undoing the multiplication by 1/2 is multiplication by 2, right? The next one, undoing -10 times row 1 added to row 3. Replace row 3. What are we going to get? So I have to undo the -10 times row 1. Undoing that, it'll be... Well, that's if I'm just multiplying the row by a constant, not doing anything else. So if I want to undo adding -10, I need to just add 10. Good. So it's 1, 0, 0, 0, 1, 0, 10, 0, 1. The third one, what's it going to be? Good. And the fourth one, we got to undo -12 row 2 added to row 3. So what are we going to have? Good. Because I have to add it. It would add, whoops, 1. Add +12, right? And then finally, the last one, we'd have 1, 0, 0, 0, 0, not 0, 0, 0, 1, 0, 0, 0, 7, right? And we would multiply the 3 together, or excuse me, the 3. Try that again. We need to multiply the 5 together and get our lower triangular matrix here. You have to do that? What'd you get? 10, 12.
In my calculator, I got 0.
Well, it can't be a 0 there because we can't have all zeros down that column. Something's not quite right. So we definitely get 2, 0, 0 and 0, 1, 0 here. And then this would be 10, 0, 1 there. 2, 0, 0, 0, -3, 0. And then we'd have 10. Oh, goodness. My brain's not working fast enough to be able to do all that without having to write it down. So we have 2, 0, 0, 0, 1, 0, 10, 0, 1. And then times the -3. So the next one will be a -3 here instead. And then times 1, 0, 0, 0, 1, 0, 0, 12, 1.
It's a 7.
It's a 7 on the bottom? 10, 12, 7? Okay. Good. All right. Thank you. Save me for trying to do it real fast. All right. Cool. So this is your L. So then your A should be 2, 0, 0, 0, -3, 0, 10, 12, 7. And then 1, 0, 0, 0, 1, -1/3, 0, 0, 1. And then we can use this to solve the system again. If we have a system, and this is where I messed up the other day. If this is times some x1, x2, x3, when you multiply these two matrices together, you're going to have something with variables in it, right? So you might as well think of this as some variables to start with, solve for the A, B, and C, and then figure out what the x1, x2, and x3 have to be. You've got several different... Whoops, that disappeared. Why did it close it? That was weird. You have several different ways of solving systems, but I wanted to show you real quick on R how you can get an LU decomposition relatively quickly. It'll be a little bit different than what you solved because it'll keep ones on the diagonal for the L rather than the U. Okay, but if I type in that matrix, so the matrix here was 2, 0, 0, 0, -3, 1, 10, 12, 3, 12, 3. We have 3 rows, and I typed it in by row. And I mistyped because I have big fat fingers. All right, so remember pragma is that thing that gives us all those nice operations that aren't built in to start with, right? If I do LU of the matrix that I just typed in, it'll spit out an LU decomposition. Okay. Now again, notice that here's your lower and here's your upper. It looks a little bit different, but it keeps the ones on the diagonal for the L rather than the U. So again, LU decomposition is not unique. The whole point of this, though, is to help solve for save computational time if you're trying to change what the constants are in your system and you want to save. It's the same algorithm to solve every time. That's the whole point. But anyway, you can check. If you use this LU decomposition and solve, you can go through that same process and make sure you're getting the same answers. Or you can also practice and see if you can get the L's with the ones down the diagonal instead of for the L instead of the U.
What did you type into the LU? Sorry, I missed that.
Oh, it's just LU of the matrix. Okay. Yeah. Literally, and it's lowercase. It's lowercase L, lowercase U. If you type uppercase, it will give you the error. It doesn't know what that means. Okay. All right, so let me know when you're planning on taking the exam. Again, a convenient time might be just to come in early on Friday, because we won't have class Friday. So a convenient time might just be come in before class and start early, so you have time. The whole point is just make sure you have plenty of time, right? But it doesn't have to be before class and do it then. I'm just saying that might be convenient since you already have the 9 o'clock hour booked. So, all right. Have a good one. I'll be around today and tomorrow if you've got questions about stuff too.
How many proofs are going to be on the exam?
74. It'll be a couple. There'll be at least one that has playing around with the elements in the matrix, or the entries of the matrix. That's what we asked. Okay. And then some of it was like the properties. Like the last one was with the properties where you do the properties with the transpose. Yeah.
Okay.
Yep.
Thank you.
I have a
Hey,
question
yeah.
for the homework.
Okay.
There was like that one on there, and I did not know like where the
So it doesn't really matter. Okay. So I would do the same thing of trying to do the row reduction idea.
Okay.
So I would, well, I could get a 1 here, but I'm not going to bother at the point. What would I need to multiply this by so that I add it to that and make it go away?
Here's 2.
2. Yeah, so I positive 2.
Or
right?
yeah, minus 2.
Yeah.
Sorry.
It's okay. So that would keep that the same. That would make that 0. This would give me 2x minus 4. If I want to make this into the identity matrix, I have to turn this into a pivot.
Yeah.
When can't I turn it into a pivot?
Oh, when it's 2.
Yeah.
So then it's just getting it so that it's a row of zeros.
Yeah, exactly. Yeah.
Oh,
That's
okay.
exactly what I want you to do. Yep.
Okay. So then when it's singular, that means it's not possible. Non-singular means it's possible.
Correct. Yeah.
Okay.
Yeah. It's kind of backward.
Okay.
It feels backward at least,
Yeah,
right?
it does.
Yeah. Yeah.
When you do the way for the RRDS,
Mhm.
how
How
do
do
you
they?
get the example you just did?
So remember when we were writing the inverses as a product of elementary matrices?
Yes.
Okay. So we had to undo these row operations. We did 1/2 of row 1. That's why this one is 2 0 0. We're undoing it. Yeah, we're using those things. Yep. That's where it's coming from. Yep.